have a lot of fun. You can have a lot of fun with dice in a casino because there's so many different options and so many different probabilities to calculate with a pair of dice. So craps is a popular game at the casinos. Anyway, just a little bit about classical probability calculations. On the next page, if you're a little confused by the dice, I don't know if this will help or make it worse. If you need help finding those sums of 7, you can see there's 1 and 6. I think they're along the diagonal for you. Those are the 6 different options, and here's all the other 36 options that can occur, from double 1s to double 6s. Just if that visual helps. If it makes it more confusing, then don't worry about it. All right, so empirical versus classical. Again, sometimes you can only use the empirical method, and sometimes you can only use the classical method. Most of the time, these yield similar but not the same results. But the larger the sample is for the experiment using the empirical method, the closer it will be to the classical probability. And this is another demonstration of what we call the law of large numbers. There are other ways to compute probabilities. Page 241 mentions them: simulation and subjective probability. We're not going to really worry about those, but they are mentioned in your textbook. This brings us to section 5.2. So section 5.2 is about the addition rule and something called complements. And this is on pages 247 to 254 of your textbook. So the first thing we need to discuss are what are called disjoint events. 2 events are considered disjoint if they cannot both occur at the same time on the same trial. So if I flip a penny one time, I can't land on heads and tails at the same time. Those are disjoint. I either land on heads or I land on tails. They're separate, they're disjoint. Same thing with rolling a die. I can't land on a 1 and a 2 at the same time. It's either a 1 or a 2 or a 3, etc. So each side of the die is disjoint from the others. It only lands on one side at a time. So this is also called, you'll also see the words mutually exclusive. If you're exclusive, then you're excluding. So that's how I remember disjoint, excluding. So if you're mutually exclusive, that means you have nothing to do with the other. That's another way to remember disjoint. So you'll see the words mutually exclusive sometimes as well. Alright, so the book uses Venn diagrams, if you guys remember what those are, to help us kind of visualize different probabilities and kind of help us sort out what we're looking at. So the book uses an example of using the digits 0 through 9. So that'd be the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's actually 10 different digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because we're including the digit 0 in the set. So we actually have 10 possible outcomes. 10 different digits, 0 through 9. So if we pretend like each digit's on a chip, and we're going to draw chips like out of a bag, event F, we're going to say choose a number greater than or equal to 8. And then we'll have a different event E, choose a number less than or equal to 2. So this is like at a carnival, maybe with little kids, and they're picking the chips out of the bag. And someone gets a prize if they get a number greater than or equal to 8, or you'll get a different prize if you choose a number less than or equal to 2. So the event F only has the chips 8 and 9 in it. And the event E only has the chips 0, 1, and 2 in it. And then still in the sample, but not in the 2 events, are the numbers 3, 4, 5, 6, and 7. So they're in the bag, but they don't win a prize. And you'll notice that these are disjoint events. They're not overlapping. because event F, the outcomes in event F, do not have anything to do with the outcomes. Oh, y'all can't see that. The outcomes in event E. It's a little too dark. There we go. A little better, maybe. There we go. Maybe that's better. I'm not sure. There we go. Alright, so event E and F are considered disjoint. So we have what's called the addition rule for events that are disjoint. So if we have disjoint events, the probability that event E or event F occurs, you would just add their probabilities together. So probability of E or F, this is from your book, is the probability of E plus the probability of F. And that exact thing is on your formula chart, addition rule for disjoint events. So in our little chip scenario, the probability of E or F, E has 3 outcomes, 3 out of, we said 10, plus event F has 2 outcomes out of 10, which gives me a total of 5 out of 10, which we can reduce to 1/2. So half of the chips will give you prizes and half of them will not. You'll notice you have 5 on the outside and 5 total in the circles. So the probability would be 1/2 or 0.5. So it's pretty easy for disjoint events. You just take one, add it to the other, and you're done. Same thing is true if we add another event that's disjoint. So if we're adding a new event to that same scenario, and event G is choose a 5 or a 6, so we have 5 and 6 in a new circle. So now we still have event E, event F, and this new event G, and we still have some outside the sample that do not win a prize. So to get the probability of E or F or G, we're going to do the probability of E plus the probability of F plus the probability of this new event G. So E is 3 out of 10, F is 2 out of 10, and G is also 2 out of 10, which gives us 7 out of 10, or 0.7. And that should make sense. There are 7 total outcomes in the circles and 3 on the outside. So that is how you would get that probability. Pretty easy, I think. Don't overthink it. There's a lot more examples on page 249 to 250. I think it's a pretty straightforward situation, though. Then we have what's called the general addition rule. And this is for events that have what we call an overlap. So if an overlap occurs in the events, then we cannot count the overlap twice. And I don't want to be confusing about this. Hopefully the picture will help it make sense. So if we have a new scenario using the digits 0 through 9, and our event E now is choose an odd number. So let's think about that. Event E would be 1, 3, 5, 7, 9. And then event F, choose a number less than or equal to 4. So event F, less than or equal to 4, 0, 1, 2, 3, and 4. Right away you notice that the numbers 1 and 3, if you notice, 1 and 3 are odd numbers. 1 and 3 are also less than or equal to 4. So we have what we call an overlap. 1 and 3 occur in both events. And if you can see the Venn diagram, that kind of helps as well. Well, it's kind of dark. So on the Venn diagram, there we go. We have event E is this entire circle, including the overlap. That's how a Venn diagram works. So you'll see the numbers 1, 3, 5, 7, 9, those odd numbers. And then we have event F, which is this entire circle. That entire circle is event F, and it has the numbers 0, 1, 2, 3, and 4. And in the middle is where we put the overlaps 1 and 3, because they're in both. So the cat eye is the overlap where these outcomes are shared by both events. So it makes it look, they're not disjoint, they're actually overlapping. So that's why we draw Venn diagrams, to try to help us. So that same picture, we want the probability of event E or event F. So the probability of event E again, just that entire circle, pretending that event F was totally gone, the probability of event E is 5 out of 10. We have 1, 2, 3, 4, 5 odd numbers. The probability of event F is also 1, 2, 3, 4, 5 out of 10. So we have 5 out of 10 and 5 out of 10. The problem is this 5 out of 10 includes the numbers 1 and 3, and this 5 out of 10 includes the numbers 1 through 3. So we have a problem here because the numbers 1 and 3 got counted twice. So we subtract those overlapping outcomes, which is the probability of E and F, which is 2 out of 10. So if we do 5 out of 10 plus 5 out of 10, and then subtract 2 out of 10 since that got counted twice, that should give us 8 out of 10, which should make sense. 1, 2, 3, 4, 5, 6, 7, 8 total outcomes in the circles, and 2 outside the circle. So 8 out of 10, which reduces to 4 out of 10, not 4 out of 10, 4 out of 5, 4.8. So if you look at the addition rule, the general addition rule, you'll see that the probability of E or F is the probability of E plus the probability of F, just like it was, and then minus the overlap, the probability of E and F. And that is exactly how it's written in your chart. So really these are the same, these are the same formulas. This has this little bit if there's an overlap. And if there's not an overlap, then you just don't put anything there. So, those are the addition rule. Alright, so let's think with a deck of cards. Some of you might be very familiar with decks of cards. Some of you might be a little less familiar with an American deck of cards. So let's see. Here's a deck of cards I brought. And there's 52 total cards. And there's different colors and different suits and different numbers and letters. So the A is an ace. ACE is called the ace. The Q is called a queen. I'm going to take the jokers out. Jokers don't count. J is jack. Then you have sevens. There's a jack, an ace, eights, nines. There's another ace, 8, queen again. Let's see if we can find it. K is king. There's another king. There's also 4 different symbols. There's hearts, spades, diamonds, and clubs. So there's 4 different suits. The hearts and the diamonds are red, and the spades and the clubs are black. So if you're not too familiar with the deck of cards, you might just want to go to the dollar store and buy a deck, just so you're a little more comfortable. I play cards all the time, so I'm very comfortable with the deck of cards. The textbook does a nice job of organizing these 52 cards to make it a little easier for you to see. So, here's all 52 cards. We have the kings of each suit, the queens of each suit, the jacks. Then there's a 10, 9, 8, 7, 6, all the way down to 2. Ending with an ace. So we have ace through 10. Ace is kind of like a 1 through 10, and then jack, queen, king of diamonds, clubs, hearts, and spades. So again, if you're not too familiar with the deck of cards, there is a nice visual in your textbook in this section to just kind of help you get familiar. If you just go to the dollar store and get a deck of cards, it will also help you just be more comfortable with the different way cards are organized. So, let's see, what is the probability of drawing a king? If you look at your chart, there are 1, 2, 3, 4 different kings, and out of a total of 52 cards. So the probability of drawing a king is 4 out of 52. The probability of drawing a diamond. So the probability of drawing a diamond. There are 10, 11, 12, 13 diamonds, if you count 13 diamonds out of 52. So it's 13 out of 52. The next question says, are these disjoint events? And the answer is no. There is a king of diamonds. So let me find it in the deck. So those are kind of small. Let me find the king of diamonds. So if we're going through the deck, we have diamonds, we have kings, and then specifically there's one card. Where is it? There it is. There's one card that is a king and a diamond. So it was counted out of the 4, and it was also counted as part of the 13. So it was actually counted twice. So because this particular card was counted twice, we have to subtract it off so that it's not counted twice. So the probability of getting a king or a diamond will be the probability of getting a king plus the probability of getting a diamond minus the probability of getting a king and a diamond, and that will give us the probability we want. So 4 out of 52 kings plus 13 out of 52 diamonds minus 1 out of 52, which is the one we counted twice, the king of diamonds. And that should give us 16 out of 52, which reduces to 4 out of 13, which is 0.3077, and you can round that to 0.31. So a 31% chance of getting a king or a diamond when you draw a card from a deck. So that's how to work through those. Hopefully some of you are familiar with the deck of cards. If not, just go buy a deck from the dollar store. Alrighty. The last thing to discuss in this section is the complementary events. So the complement of the event is the probability of the event not occurring. So the complement of the event rolling a 1 on a dice, here's a die rolling a 1, the complement of it is not rolling a 1. So I either roll a 1 or I don't roll a 1. We use the notation, let me turn the slide off, we use the notation E for event and a superscript C for complement. So it's EC for complement. Maybe that lamp's helping. Alright, so E to the C, superscript C, means the complement of the event or the event not occurring. So let me show you a couple examples of that. So if the probability of rolling a 1 on a single die is 1 out of 6, the probability of not rolling a 1 is 5 out of 6. Because there's 5 other options that are not 1s on a die. So these probabilities will always add to exactly 1. So the probability of an event occurring plus the probability of the event not occurring will always equal 1. And the way the book writes this, let me show you, all it's done is subtracted this one and put it on the other side. Just one basic algebra move. So the probability of the complement is 1 minus the probability of the event. You could also say the probability of the event is 1 minus the probability of the complement, which we'll see a little bit later in section 5.3. So that is the complement rule. And let's see. That is at the top of the next page of your formula chart, the complement rule. We are not going to be covering those last 2 bullets, and we're not going to be covering anything over there. So we're going to stop after the multiplication rule. That's the second half of chapter 5 that we're not covering. But there's the complement rule at the top of that second page. All right. So far, so good. Let's see how this looks. So the book does a nice visual. Here's the event, and here is not the event. So this would be like roll a 1. Here's the event rolling a 1. Here's the event not rolling a 1. So every other event that's not rolling a 1 would be on the outside, and the whole space is the entire sample. Alright. So earlier we computed the probability of rolling a sum of 7 on a pair of die to be 17%. So if we call that probability of S, what is the probability of S complement? So if the probability of S is 0.17, the probability of not S is 1 minus 0.17, which is 0.83, or 83%. So if you have a 17% chance of rolling a sum of 7, you have an 83% chance of not rolling the sum of 7. This saves you time of adding up all the rest of them, or you can just subtract the percentage from 1. Some students see it better that if you have 6 out of 36 that work, then 30 out of 36 don't work, which will also work out to about 0.83. So that's how the complement rule works. It saves you a ton of time, especially in more complicated situations, which we'll see in section 5.3. All right, another example. So again, this probability model, let's just say it's different colors of M&Ms from a regular sized bag. So this particular bag had no reds. So these different probabilities of different colors of M&Ms. You randomly select an M&M from the bag. What is the probability of not getting a yellow M&M? So you could sit there and add up all the other probabilities other than yellow, or you could do 1 minus the probability of getting a yellow, which would be 1 minus 0.15, and it's very quick to get 0.85, or 85%. So it's faster to subtract what you do not want and to get what you want, which we'll see again a little bit later in section 5.3. So that's just a quick way to get answers without having to do extra work. I'm going to pause here and then I'll pick up with section 5.3.